going to be about Chapter 26, Section 3, Thin Film Interference. Thin film interference is exactly what it sounds like. If you have a puddle of water and there's a thin film of oil across the top of it, you may see what looks like a rainbow of colors. And what's happening is certain colors of light are being constructively interfering with each other, so you may see more yellow or pink or blue, and other colors of light are destructively interfering. We also have this with like coatings on eyeglasses. The eyeglasses that I'm wearing have a non-glare coating to help cancel out not all of the light that's reflected off of it, but much of the light that reflects off of them. Let's think about what happens when light hits a surface. So here is a situation where we have air, and then we have a thin film. This could be like a soap bubble, and then another layer of air. So anytime you see, if you've ever gone outside and played bubbles and you see kind of that rainbowy look on the surface of the bubble, you've got a situation where you've got air, and then this little layer of soap, and then more air. If we were looking at maybe a puddle on our driveway, we might have air and a thin layer of oil and then water. We're going to look at this example first. We know that this has an index of refraction of 1. We know that this has an index of refraction that's greater than 1, simply because anything has an index of refraction greater than 1. Certainly soap does. And this will have an index of refraction of 1. I want to consider this to have a thickness of T. Now, I could try and draw light absolutely perpendicular, which would be the ideal, but then we can't really see. So I'm going to draw the light where it's not quite perpendicular, but I want you in your mind to think, oh, what if it was truly straight up and straight down? So if I have a beam of light and it hits this surface like this, some of the light is going to just reflect straight off. Some of the light is going to go refract toward the normal, bounce off, and then come out. Now, if I could have drawn it perfectly perpendicular, all of this light would go straight down and straight up, but you wouldn't be able to see the two different rays, and I want you to see what happens to those. Because this one hit an index of refraction that had a higher, it went from a low index to high index. When it bounces off a higher index of refraction, it undergoes a 1/2 cycle phase shift. So this first ray had a 1/2 cycle phase shift. Now you might wonder, well, why in the world did it have a phase shift? Well, it had a phase shift for the same reason that if I send a wave pulse and it hits a rigid boundary, I don't know if you remember when we talked about waves, when it bounces off, it's reflected. It undergoes a 180-degree phase shift. Okay. That only happens, however, when it reflects off a higher index of reflection. So, when light reflects off a surface with a higher value of N, so it's in some medium with a lower value, and then it hits a higher value of N, it undergoes a 1/2 cycle Now, half a cycle is 180 degrees or pi radians, a 1/2 cycle phase shift. So that this first ray the one that bounced directly off the film, had a half cycle phase shift. The second one, the one that went on into the film and was refracted, did not, because it went from film to air. Well, that's not hitting something denser. So the second one had no phase shift. So you have to pay attention. Sometimes what you're going to see when you do these problems, you can have situations where there's no phase shift at the top and no phase shift at the bottom, depending on the indexes of refraction. Or if we had gone from air to film to a piece of glass, which had an even higher index, you might get phase shifts at both surfaces. It's probably pretty typical to, if we start with air, which always has n equal 1, chances are we're going to either get a phase shift at one of the surfaces or possibly a phase shift at both of the surfaces. So what's that mean in terms of constructive or destructive interference? Okay, well, let's think about this. It really all comes down to how thick this film is. Okay, in this case, since we already have a half cycle, they're off by 180 degrees between their two phases. In other words, if this didn't exist here, remember, anytime you have light that's exactly out of phase by a half cycle or 180, we expect to get destructive interference. However, this second one is traveling a longer path. The top ray, maybe I should, is doing that, but the part that got refracted is traveling much farther. How much farther? Well, it's traveling 2t farther because it's going here and back. So if 2t is equal to one wavelength, if this thickness is exactly one wavelength, they're still going to be exactly one half cycle out of phase. If we had 0 wavelengths, like right here, they'd be completely out of phase. But if this 2t is a whole number of wavelengths, whether it's one wavelength or 2 wavelengths or 3 wavelengths, so what we see in this situation, that we are going to get destructive if 2t equals a multiple of the wavelength. But we have to be really careful which wavelength. A multiple of the wavelength in the film. Remember, wavelength changes when you go from air into another material. Okay? So we need to kind of summarize this in a way that makes really good sense. We know that when light hits a more optically dense medium, it will undergo a phase shift. In this case, when it went from film to air, if it hits a less optically dense or a lower index, there will be no phase shift. So what's that mean in terms of destructive and constructive? In this case, destructive is going to happen anytime this thickness, twice this thickness, equals a whole number of wavelengths. That means that constructive interference is going to occur anytime this thickness is equal to an odd number of half wavelengths. Whether it's just, if 2t equals a half a wavelength, or if 2t equals 1.5 wavelengths, or if 2t equals 2.5 wavelengths. So it's an odd number of half wavelengths. Okay. Let me kind of summarize this with some rules, and then we want to work some examples. Okay. When light is incident on a thin film, both or neither of the waves have a half cycle shift. So that means either neither one of them are reflecting off something with a higher density, or more likely both of them are reflecting off something with a higher density. But either case, they either both have a phase shift or neither one of them has this phase shift. Then we're going to skip the situation where we have constructive anytime 2t is a whole number of wavelengths. And we're going to get destructive any times 2t is equal to m plus 1/2 wavelengths. If only one wave has a half cycle shift, it's going to be just exactly. If both waves are not experiencing the same thing, like the one that I drew where the upper surface had a half cycle shift, but the lower surface had no shift, if only one of those, then constructive means that 2t has to equal m plus 1/2 a wavelength, and destructive occurs when 2t is equal to a whole number of wavelengths. In either case, remember that the wavelength we're talking about is the wavelength in air divided by the index of refraction, because the wavelength in the film will be different than the wavelength in air. So when we talk about multiples of the wavelength, we're talking about the wavelength that's in that film. Okay, let's look at some examples, because when I do examples, this will be pretty easy to understand. You will have to stop and think on each problem. Is a wave being shifted or is the wave not being shifted? And then what do I need to happen? Am I trying to get constructive? Am I trying to get destructive? I didn't see any great examples in the actual chapter, but there were a lot of good problems at the end. So this is from page 854, problem number 15. And it says it wants to know the thinnest film that appears black. Well, if the film appears black, they're really talking about destructive interference happening. When viewed by reflective light, I'm going to leave out some of the words, that has wavelength equal to 480 nanometers. And they're talking about the wavelength in air or the wavelength in a vacuum. They tell us that this is a soap bubble, and the soap has an index of refraction of 1.33. So our situation here is we have air n equal 1, then we have a thin film of soap n equal 1.33, so that's the same as water. Most soap is mostly water with a little glycerin or something. And then we have air. So there's our soap bubble. We need to think about where we get a phase shift and where we don't get a phase shift. I'll try, I think, maybe 2 different colors to help with that a little bit. 480 nanometers is actually probably up in, I'm going to say, in the blue range or almost to the violet range. So here's air coming in. Part of the light reflects off the upper surface, and that part is shifted by 1/2 cycle because it hit a higher index of refraction. Part of the light actually is refracted. It continues into the film. It does not, however, have a phase shift when it reflects here. So this is no phase shift. Now, like I say, I can't really draw it. If I could draw it vertically, you just couldn't see much because what would happen is I'd have a picture that would look like light came in and light went out and light went in farther and light came out farther. But it's these two waves that really are coming out like that are going to interfere with each other. Well, we can see when we look at this that we get destructive. These come out exactly a 1/2 cycle out of phase. That's what we want, but their distances are not the same. This one in the film travels a distance of 2t farther. It's that extra distance, this is t from above. This is a distance, a thickness of t. So this bottom one, the one I drew in pink, travels a distance of 2t farther. If I want to maintain the fact that they are still going to be exactly a 1/2 cycle off, which was what I want if I want destructive, then I need this extra distance to be a whole number of wavelengths. I need it to equal m lambda. That will give me destructive. Because let's just say, if this ray from here to here travels 100 wavelengths, I want this one to travel 101 wavelengths. But notice they'll be off. Okay, so now I just need to go, I got the right formula. I need to find my wavelength. I know that my new wavelength while I'm in the film is 480 nanometers divided by 1.33. And I'm going to do for the thinnest possible film, n will equal 1. I just need to know what 480 divided by 1.33 is. Comes out to be about 360.9. So when I divide by 2, I get 180 nanometers. Notice we only had 2 significant digits here. This worked out pretty nice. That's the thinnest film that will make that soap bubble look black. It's not the only thing. We could have done 2 or 3 or 4 or 5, but those will give us larger thicknesses. So that's our first example. And that's an example where we were after destructive interference. Let's do another one where we're after destructive interference, but where the situation is somewhat different. That's actually not different at all. Let's do this one. This is problem 8 on page 854. Also, this is number 15. Nope, number 19. And it has a pair of binoculars, and these binoculars have a coating on them. So here's air, and then there's this coating, and then there's the glass. So we have like glasses or something else that's got a thin coating of some sort. So our index of refraction is 1. The coating on these glasses has an index of 1.38, and the glasses themselves have an index of 1.52. What we see here, and we can ask lots of different questions though, is a ray of light that's pretty much perpendicular comes in. It will have a 1/2 cycle shift. Normally, if it's coming from air, it doesn't matter what it hits, it's going to have a shift. But notice this time, the glass has a higher index than this coating, so we get a second shift. Whoops, that should be towards the normal. We get a second shift here, also a half cycle. So we can see, since they're both going through a half cycle, we will be in phase if this thickness, if two of those is a whole number of wavelengths. In other words, if the extra distance traveled comes out to a wavelength, they'll still be in phase. So if 2t is equal to m, I'm hoping everybody understands. Remember when we did the problems like this, where we had two sources and here's point P? And we said anytime R2 minus R1 was an even number of wavelengths, they arrived in sync. In other words, if this extra distance was like 1 or 2 or 3 wavelengths, they would arrive in sync. Well, that's the exact same thing we're doing here. This beam of light that travels into the film and then reflects off the surface of the glass has covered an extra distance of 2t, and we want that extra distance of 2t to equal a whole number of wavelengths if we want them to be in phase. If we want constructive, that's what we'll get. If we want destructive, we need those to be out of phase, which means we need this. Okay? And we can do it either way. Suppose that we want to create a non-glare coating on these binoculars. If I want a non-glare coating, then I want destructive interference. The thinnest possible non-glare will be at m equal 1. So if I want a non-glare coating, and I just want to pick, say, a wavelength of light in the middle somewhere. So we'll say for light equal 525 nanometers. Remember, most of the time in real life, we're dealing with white light, which goes anywhere from 400 to 700 nanometers. So typically, when they design non-glare coatings and things, they aim for the middle, somewhere around 550. Okay, so in this case, we're using 525. If I want to have a non-glare coating with the minimum thickness, then 2t would have to equal 1/2 the wavelength, but not 525 nanometers. The wavelength in the coating, which would be 525 nanometers, divided by 1.38, because that's the index of refraction of the coating. The wavelength in the coating is going to be smaller. So in this case, T is 1/4 of whatever that wavelength is once you divide. So let's see. 525 divided by 1.38. And that comes out to be 95.1. Now, it's possible that that thickness would not be thick enough to be durable, and they might want to use a thicker coating. If they wanted to use a thicker coating, instead of putting a 0 here and having a 1/2, we could put in a 1 here and have 1.5 and make a thicker coating. Let's try that. 525 divided by 1.38. In that case, you could get similar results with a coating of about 285 nanometers. And that might be more practical to have a thicker, more durable coating. But actually, neither of those are the questions that were asked in problem 19. In problem 19, they said that the wavelength of 525 reflects most strongly. So they're telling us this wavelength of 525 has a very positive or constructive interference with itself, and they want to know how thick, what the minimum possible thickness of the film is. Well, if this is constructing positively, we know that happens at 2t equal m lambda. And in this case, in the material, that's 525 nanometers over 1.38. We know n is equal to 1. So the minimum thickness that will give us constructive interference, 525 divided by 1.38 divided by 2, is 190 nanometers. And that's the actual question to the question they ask. Okay. So I hope you understand the real important ideas of thin films. First of all, you need to understand when you bounce off something with a higher index of refraction, you get a half cycle shift, whether it happens here or whether it happens here. When this second one emerges, it could possibly be in phase or out of phase, depending on how much farther it has traveled. Okay? If these are the same, then I want to get a multiple. 2t would have to equal a multiple number of wavelengths to maintain that they would come out in phase together. That's our constructed right there. If somehow this extra distance traveled came out to be m plus a half wavelengths, they would come out exactly out of phase. All right, I think I've repeated myself on thin films enough for today. The next section, I believe we're going to start looking at diffraction patterns.